Neutrinos can be considered as special particles under a certain point of view. They are elementary fermions which are exceptionally elusive and penetrating, capable of traversing the Earth unaffected. This puzzling property comes from the fact that neutrinos do not carry color and are electrically neutral. Hence, they do not feel the strong nor the electromagnetic force and interact only via the weak force. Neutrinos are also very light, practically massless, and so far, no one has succeeded in measuring their absolute mass. It is impossible to directly detect a neutrino since it does not ionize when it crosses matter, nor does it deposit its energy in a calorimeter. We can detect neutrinos only indirectly when they rarely interact with matter and produce secondary particles which can be detected and measured. By crossing symmetry where ingoing particles are replaced by outgoing antiparticles, the free neutron decay implies the existence of two other related processes, the electron capture (EC), and the inverse beta decay (IBD). An antineutrino is involved in the IBD process, while the interaction of a neutrino on a neutron would give an electron and a proton in the final state. This is called quasi-elastic (QE). The inverse beta decay reaction has played a crucial role in many experiments. When an antineutrino interacts with a proton, a positron and a neutron will emerge. Both particles can be experimentally detected, providing a unique signature for the event. In 1956, more than 20 years after Pauli's postulate, neutrinos were first successfully detected in the experiment of Cowan, Reines, Harrison, and Kruse. In late 1951, Reines and Cowan began a project called Project Poltergeist, the first experiment in neutrino physics. The idea for detecting the neutrino was to detect both products of inverse beta decay. The incident antineutrino interacts with a proton with the emission of a positron and a neutron. The reaction takes place in a liquid scintillator. Shortly after it has been created, the positron annihilates with an electron, creating a back-to-back pair of gammas. This will cause the liquid scintillator to produce a flash of visible light. In the meantime, the neutron wanders about following a random path until it is captured by a nucleus. To enhance the capture signal, cadmium chloride is added to the liquid scintillator. Cadmium is a highly effective neutron absorber and gives off a gamma ray when it absorbs a neutron. The arrangement was such that the neutron capture occurred with a lifetime of 5 microseconds after the signal from the positron annihilation. The neutron capture on CD releases about 9 MeV of energy in gamma rays that will again cause the liquid to produce a flash of light. This sequence of 2 flashes of light separated by a few microseconds is the double signature of inverse beta decay. The entire detector was surrounded by a lead-paraffin shield and located underground, nearby a reactor at the Savannah River plant. The reality of the neutrino had been proven.